Thank you for your kind presentation and good afternoon to everyone. Today I'm going to show you our numerical results about the crack-induced degradation of vibration characteristics in FRP-plated reinforced concrete elements. This work has been carried out with the contribution of Professors Greco, Lonetti, Luciano, and Nevone Blasi, and Doctors Pranno and Maio. We know that in the last years, structural health monitoring is gaining more and more importance in order to avoid the risk of catastrophic failure in existing structures. In the classes of damage detection methods, vibration-based techniques are based on the concept that the damage will alter the dynamic properties of the system. And it is possible to detect the occurrence of damage phenomena by measuring the dynamic structural response. To the vibration-based methods belong the data-based and the model-based techniques. The first one are based on statistical model of the extracted from time history responses, while the second one are based on physical models of the monitored structure. We then saw the structural health monitoring procedures based on the coupling between numerical models and experimental data. Our approach has been implemented into a 2D finite element framework. And in order to take into account all the complex nonlinear phenomena such as concrete crushing, rebar yielding, and FRP debonding, we incorporated two different submodels. The first one, known as diffuse interface model, and introduced by some of the authors, is able to reproduce the crack onset and propagation in the concrete phase and FRP debonding phenomena by the insertion of cohesive elements along the boundaries of the finite element mesh and along the material interface between concrete and the reinforcement system. The second submodel, instead, called embedded truss model, is able to reproduce the interaction between concrete and steel rebars. Our numerical simulations involve a 4-point bending test performed by Amado and co-author in 2015. Preliminary, we analyzed a reinforced concrete beam without FRP system, without any reinforcement system. So we evaluate the ultimate load, and we define 9 unloading levels as a fraction of the failure load. We can see that each unloading path exhibits residual plastic deformation. And for higher damage level, for example, from L6 to L9, we can see that each curve has two different slopes that are related to the combined effect of the concrete plasticity and the partial contact between the crack faces, which cannot completely close to the presence of aggregates and the sliding phenomena that occurs at the concrete rebars interface. After the static analysis, a linearized eigenvalue problem has been solved by performing the analysis of small amplitude free oscillations superimposed on the damage scenarios obtained at the last point of each loading path in order to take into account all the complex nonlinear phenomena previously introduced. So we can see on the left of the slide the degradation of vibration frequencies for 7 selected mode shapes, and on the right we can see a comparison between the experimental envelope and our numerical model of the frequencies for the first mode shape. After the validation procedures, an FRP strengthened reinforced concrete beam has been analyzed with the same methodologies and procedures used on the control beam. We added 3 new load levels in order to capture the rebar yielding and FRP phenomena, the bonding phenomena. And we can note immediately that after the yielding phase, each curve exhibits low residual plastic deformation compared to the control beam, due to the strengthening effect provided by the FRP that influenced the global stiffening of the beam. Instead, after the yielding phase, we can see, due to the nonlinear phenomena such as the concrete plasticity and the partial contact, we have big residual plastic deformation. Solving the linearized eigenvalue problem for the FRP-plated beam, we can see in this slide the reduction of the normalized frequencies for 4 selected mode shapes. And we can see that each path has 3 different slopes. The first one that is related to the elastic stage, the second one that corresponds to the crack formation stage that is characterized by a fast evolution of the damage processes, and the last one that corresponds to the stabilized crack phase. And then we can see that after the yielding load, the frequencies drop with a steeper slope up to the peak load. Finally, we evaluated 2 of the most common damage indicators available in the technical literature. The first one is the modal curvature. Analyzing, for example, the modal curvature for the first mode shape, we can see that in the early load levels, the changes in the slope that indicate the presence of damage are in the central part of the beam. Subsequently, the effect on the FRP that is mainly provided in the bending zone limits this change, and the peaks are registered in the lateral part of the beam. However, it's important to note that the modal curvature influences the fracture process near the beam support and near the plate end influence the modal curvature for the high order mod shape, because we can see higher peaks in the lateral part of the beam where no really damage is present. So to overcome this issue, we need another indicator that is not focused on a single mod shape, but that are based on the summation all over the investigated mod shapes of the absolute differences between the modal curvature obtained at the generic coordinate. And this is the curvature damage factor, because we can see in this slide that the peaks are proportional to damage and therefore to the crack length. So in conclusion, we proposed a numerical model that, with a properly calibration of some parameters, is able to take into account all the typical nonlinear phenomena that are induced by cycling loading conditions, that are the loading condition really present in existing structures. And in the light of the obtained results, we can conclude that our numerical model could be a useful tool for the damage detection in a reinforced concrete structure, also strengthened with FRP. Thank you for your kind attention.